Hey everyone, this is Kyle Miller, Solutions Engineer at DJI, and today we're going to talk a little bit more about DJI's Zenmuse L1 Lidar platform. So diving directly into what is the L1, some of the aspects, the highlights that we want to focus on are instant clarity and superior accuracy. You're going to see why we mention instant clarity in a little bit later, as well as that superior accuracy. So how to get a very dense point cloud out of a LiDAR solution compared to photogrammetry, and how to make sure that that LiDAR solution is accurate using a couple different software and hardware features. So we're going to dive into why the L1 solution overall is a great budget-friendly entry-level LiDAR solution that's going to help be scalable across your organization and be able to help get more LiDAR solutions on the job site. We're first going to talk about the actual L1 payload, what it all has on board, what are some of the features, selling points, as well as getting into the applications and then the use cases of LiDAR on some of the commercial job sites that we work on. So talking specifically about the L1 is a highly integrated, cost-efficient enterprise aerial LiDAR payload. The all-in-one Zenmuse L1 solution integrates a Livox Lidar sensor, a high-precision IMU, a 1-inch CMOS visual camera with a mechanical shutter on that visual camera, all with a 3-axis gimbal module. When you include all of those aspects, the DJI L1 is by far the most affordable and most scalable solution that's going to be able to incorporate everything. You obviously need to have a LiDAR sensor of some sort. We're using a Livox sensor in ours. You do need a high accurate IMU for your LiDAR. If you don't understand the actual movement of your sensor to be able to, when you're going to process, be able to align the strips that you're capturing of that LiDAR perfectly, without a high accuracy IMU, your results vary and can be pretty much unusable. We also have that 1-inch CMOS sensor because we want to make sure we can colorize that point cloud at the same time as we're capturing LiDAR data. We'll talk about colorized point clouds in a little bit. And then also the 3-axis gimbal module. Think about this, if you're the other airborne LiDAR solutions that are out there, most of them, they're just mounted on the bottom and they're facing straight down, which is great for a lot of different use cases for general topography mapping. But if you are trying to do any sort of facade inspection, or if you're going to do cell tower or even transmission line, and you want to be able to gimbal up, the L1 solution with a 3-axis gimbal is going to be really, really beneficial. So all of that LiDAR solution combined with the DJI Matrice 300 RTK, you can see in the back here that we'd be able to mount the LiDAR onto, as well as processing in DJI Terra. It provides that highly efficient all-in-one LiDAR solution. Let's talk a little bit more about what specs that we typically talk about with the L1. So it's all-in-one, it's a high accuracy. You can see the vertical and horizontal accuracies that we typically are working with. High efficiency, looking at very large survey areas on one single flight. If you're using a side overlap, that about 50%, which we'll talk about in a little bit. Looking at 200 plus acres per flight potentially. High density, so you're looking at 240,000 effective points per second. That's the max on a single return, on any return, but we have an maximum output total of 480,000 effective points. So on those dual and triple returns, you're getting a very dense point cloud. We do have multi-return, so supporting up to 3 different returns. Long range, 450 meters max. With most of the flights that we're doing in the United States, we should be good underneath that 400-foot ceiling with the LiDAR payload that we have. It's also much like the Matrice 300 IP54 water dust resistance. The actual components of the LiDAR payload, if we take a look at them a little bit more, you can see on the top, obviously, is that 3-axis gimbal, how it's connected to the Matrice 300. We also have a high precision IMU. We will talk a little bit more about what an IMU is in a bit. We also have underneath or behind that greenish bluish mirror, you're going to see the mid-70 Livox Lidar sensor. And then below that is going to be the 1-inch CMOS visual camera. That's going to help colorize the point clouds. It's actually the same sensor that comes out of the Phantom 4 RTK. Let's dive into each one of those individual components a little bit more. So the actual Livox or the LiDAR sensor that we have inside the L1 is a frame LiDAR. It's about a 200-meter measuring range at 10% reflectivity. We will be talking a little bit about what reflectivity means on a later slide, but a very deep measuring range should fit most, if not all of your needs, especially here in the US. Supports up to 3 returns, so you can have single, dual, or triple return. 240,000 effective points per second on single or dual. So on dual, you're getting 240,000 points on the single, and you're getting another 240,000 points on the second return, and so you're getting a max of 480,000 points. If you do have it on triple return, we do bump the rate down to 160 kilohertz or 160,000 effective points per second, but you get that you get that on every single return of those 3, so it adds up to 480. Field of view, 70 degrees, a bit wider than your traditional photogrammetry sensor. And then there's 2 different types of scan patterns that our sensor can do, whether it's repetitive or non-repetitive. So I'll go ahead and show a quick video of what the difference is. So repetitive, that's going to be most common. It's going to be your topography mapping from straight down, but you can turn on non-repetitive scan if whatever analysis that you would like to do or whatever processing you'd like to do requires non-repetitive. That's just capturing as many points as possible across the entire field of view, and rather than just going in a line, so it almost looks like a petal, like a flower, if we were to slow it down on how it's capturing points. Reflectivity. So let's talk a little bit about different types of surfaces. What we have found is the L1 measuring range at 200 meters is about 10% reflectivity. Reflectivity refers to the ratio of reflected laser energy over incident laser energy. Different objects have different surface reflectivity. So if we look at a couple examples here below, we can see the reflectivity on most ground type surfaces, 10%. So we're looking at grass, dirt, things like that. That can absorb quite a bit of that laser energy. But if you're looking at hard surfaces like the building surface or coal or asphalt pavement, you're going to have a higher reflectivity percentage because you're being able to rebound more of that energy. You can see some more examples there below on what different surfaces have different reflectivity ranges. And return modes. Let's talk next about what those return modes mean and why. So if we are trying to be able to penetrate through some vegetation, and which happens pretty often in forestry and topography and elevation mapping, trying to create a really good digital terrain model. If you want to be able to penetrate through the most amount of vegetation, typically what you want to measure is multi-returns past that first one. So you can see the picture on the bottom right corner of a tree. You see the first return having the largest amount of energy that we're measuring back. The second return and the last return have a bit less energy, but we are picking them deeper in the canopy, potentially off the ground. So it's the one advantage that you have over photogrammetry is being able to have laser and have that laser bounce off of multiple things before coming up and measuring it. So each one of those returns is logged and viewable within DJI Terra when you go ahead and process the data. When we look at the actual camera, because we need to be able to colorize this point cloud, you may have seen this camera before, but it's actually the same from the Phantom 4 RTK, which is perfect. It's a 20 megapixel sensor. It's a 1-inch CMOS sensor, so it's pretty good quality. It's also mechanical shutter, so it is really made for mapping. And you can, on Pilot 2, set it up to just do a mapping mission if you don't want to capture LiDAR and you just capture the RGB sensor in a pinch. But we do have the ability of capturing both at once, which is a great selling point. You can capture LiDAR and you can capture the visual to help colorize it in one flight. Other solutions, you may have to fly the same flight plan twice to capture LiDAR and visual and then merge them together. But with this, it's all integrated on one payload and you can capture it at one time if you want to, or turn off whichever sensor you would like. We also have another component of the L1 is the IMU, a very important part. The IMU is there to basically measure the movement of the sensor. We're not just utilizing GPS, but we need to see all the very minute measurements. Now, the gimbal does help smooth some of that out, but if we're able to log what the sensor is doing and match it up post-processing with where the sensor is and what it was doing with the output that it came out with, that's how we get really accurate data. So you can see some measurements here depending on RTK or PPK workflows on some of the accuracies that you should be able to achieve. Operation efficiency. So now that we have talked about the payload, let's talk about going out and planning a mission and what some of the parameters would look like. What we would recommend is a flight altitude of 50 to 100 meters, which is about 160 to 328 feet, and the side overlap being about 50% minimum on the LiDAR side. Obviously, these are recommended. Depending on the use case, you can go beyond these recommended parameters, but this is what we would say to make sure you get good outputs. The one thing about the side overlap, notice that it says 61% for visual. Since the sensor has both of them on board, you can't change both the field of views. You kind of have to change one or the other. So when you're capturing LiDAR, if you set it for 50% minimum, you're going to be a bit shy for capturing enough visual to fully be able to stitch a map just on visual. Oftentimes it doesn't matter because you're just using that visual imagery to colorize the point cloud. But if you do need to also use photogrammetry and stitch just the visual data together, you might need to bump up that side lap ratio. Flight velocity, we would typically recommend 5 to 10 meters per second, depending on your flight altitude, closer to 5 meters per second when you're at that 50 meters or 150 feet. Now, comparative to photogrammetry, flight speed and the side lap are very, very, very important. With flight speed, you're talking about what a LiDAR sensor is able to do with how many points per second. So you slow down the drone and you slow down that LiDAR sensor, it is able to gather more points over the same area because it's flying over that same area a little bit slower. So if you need to build a much more dense point cloud, you can bump that flight velocity down and get a much more dense point cloud. So process efficiency, you're going to get a live point cloud preview, which you'll see here in a minute, but then also to post-process the model. Typically, LiDAR takes less time to process than photogrammetry or traditional photogrammetry. The result, with about a single battery flight, we're going to look at about 180 acres, and with that, about 147 points per square meter. That's flying at that 328 feet and flying at 10 meters per second. If you need it higher, slow down and potentially fly lower. Let's talk about what that workflow is then, now that we understand some recommended parameters on going out and capturing the data. The UAS platform, obviously we need something to fly the L1 solution, so we have the DJI Matrice 300 RTK, and it's hot swappable. You can easily use the Skyport there. We also are using the DJI Pilot 2 app that's going to be on the M300 controller. That's going to be doing all of your automated and manual missions. You post-process the data in DJI Terra, and the ultimate output is to get a point cloud in an LAS file format, which is pretty standard, pretty typical. The data acquisition side, we have 4 different options. Really, we have actually 5, but we'll start with the 4 pre-planned ones. You can do mapping mission or corridor. Those are going to be the most common flight plans for LiDAR. Mapping mission for general topography, but corridor, we've got a lot of users using LiDAR for doing telecommunications, so line inspection, vegetation encroachment, rail inspection, where photogrammetry is not going to be able to get and map and model all of those thin cables and wires. So a lot of corridor flights are happening. You can do it for the oblique capture, but I really would not recommend it. And then waypoints, you also can do just set manual waypoints and capture the L1 or capture LiDAR with manual waypoints. I would caution you though for that. There are some very specific needs there for the waypoint flight. You do need to do IMU calibrations before, during, and after flight, and mapping missions and corridor missions automatically build in those IMU calibrations. Waypoint missions, you'll need to plan in some of those calibrations to make sure that your data is good. But you could have it just say to go here, 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 and here, and go and capture LiDAR across that line. When it comes to processing that data, we will cover this a little bit more on a later slide, but you'll be able to take the SD card out of the L1, put it into your computer, launch DJI Terra, select LiDAR point cloud, and then start processing that data very easily. While you're flying, you're going to notice a couple different things. So we've kind of talked about planning the mission, but when you've planned the mission, you're at the site, the drone is on, you're almost ready to go, you just turn the drone on, but what you're going to notice is you have a caution, an issue with your L1 payload, because typically a lot of LiDAR units, that IMU needs a bit to warm up and calibrate. So the way that we tell you that information back is through the HMS Payload Health Management System. So on the Pilot 2 app, you'll be able to click into this health management system. You can then see the payload. You can see if it has any cautions or if it's ready to go. If it does have cautions, you can tap into it and see what the problem is. That's going to save a lot of time and a lot of headaches for going out and making sure that you're capturing the data and not going back to the office and start processing it before you realize that something was not right with that LiDAR payload. So you're getting to know that before you actually take off, and you're getting to know if the IMU calibration is good enough and is ready to go. We also have a couple different views during flight. We have in the FPV, you can see on the right-hand side and the very top, the left view is just the RGB or the visual view. So while it's flying, you're going to obviously see that move. But on the right-hand side, that is the LiDAR point cloud that's getting stitched in real time. So you can either view either one of these two map layers or view layers on full screen, or you can view them like I am now on side-by-side mode. And then when you're viewing LiDAR, there's a couple different modes that you can view under. Right now, I'm viewing height, so you can probably see it in the upper right. It says color and status. It says height, so I'm trying to understand the height difference between trees and the terrain. And then also you can click into to understand the reflectivity rate. You can also look at the visible point cloud that's going to be processed real time. On the bottom side, you can also view more of a whole map view, so you can see the entire site and how that's getting processed in real time. So once again, another great tool to help understand if you're capturing the correct data before you go back to the office to process the data, so you're not losing time on the job site. And one last factor during flying I would recommend discovering a little bit more is terrain following. Why is terrain following so important? Well, with LiDARs, especially if you're varying the height above the elevation that it's capturing over, if you're just flying the same elevation from the home point, but the terrain, especially in corridor missions where you have stretches that are a couple miles long that could have hundreds of feet of elevation change, you want to make sure you capture the same height off the ground. That way you have the same side lap ratio, so that strip alignment goes well and you have high accuracy, as well as making sure that you don't have any sort of incidents and you have enough overlap to even stitch. So we do have a couple options here. The Matrice 300 has obstacle avoidance, so if it does see anything, it will stop and just kind of hover and wait for you. We also have the DJI CSM radar on top to help with millimeter wave for extra obstacle avoidance, especially around those power lines that you may be flying, especially with LiDAR that we typically do in transmission lines, to be able to avoid those. But the best way to avoid anything is to make sure that you have terrain following enabled and that you're flying the same elevation off the ground. There's two methods to terrain following. One, the quick and dirty method, if you have internet coverage at some point, is to download from the internet. So the right-hand side, you can see that there's a IMU calibrations on, the terrain follow, that toggle is on. I can then select the DSM file. If I select on that, I can choose download from internet, and it's going to download from a source that we have, ASTERGDEM v3. It's about a 30-meter resolution. So some downsides there, low resolution, and you don't know how old that DSM is. That could have been satellite data captured last week, or it could have been a year ago. And so the age, the resolution of that is a bit difficult, but the advantages are you can just show up and it's there. So on those sites that are pretty flat, that can typically, you can get by there. But if you are wanting really accurate elevation terrain following, you can go out and scan and fly the survey beforehand or the site beforehand, or if you already have it surveyed, you can load in the DSM file in a TIFF file format, and then you can see there's a yellow bounding box where I'm allowed to fly and make a mapping mission where I have elevation data, and then in the blue polygon where the flight lines are, that's where going to be all of the elevation change. You can see a graph at the bottom showing you the different elevations. So very accurate to make sure that you're getting very accurate outputs. It's one of those really crucial things to understand. And hopefully we make it pretty easy for you. So you've gone out there, you understand the platform and you understand the payload, you understand flight parameters, you've now built the flight plan, for your use case, you've gone out there and you've captured that data, you pull the SD card out, and now you are ready to process your LiDAR data. You can utilize DJI Terra. It's a Windows-based platform program that you're going to be able to download and install on your computer. You get DJI Terra free with every LiDAR L1 payload that you sell and or buy. The only difference is you get the LiDAR free service forever that's going to be able to take your data from the SD card and output an LAS point cloud. It's not going to be everything stitched perfectly together. You're not going to have strip alignment and all of that other thing, but you can at least get LAS out. Now, if you do want to process your data within Terra, we do give you at least a couple months, up to a year potentially, I think last was 6 months, to be able to have a paid DJI Terra account that's free that you get with the LiDAR purchase, and you can do all the analysis in there. But if you just need the LiDAR LAS out, you can then upload it to Rock Robotic, or you can process it in Terra Solid and get good outputs there. But when we're in there and we've processed the data, there's a couple different views that we have. We can, we can go ahead and view the RGB. So that's going to be the colorized point cloud. So we have the point cloud captured by the LiDAR, and then all of the images overlaid on top. You can also toggle to the reflectivity, so that's giving you that surface reflectivity percentage. The height, so that's going to be a little bit better for understanding power lines, transmission lines, if there's any sort of vegetation encroachment. And then return, you may saw the entire map is pretty much blue except for some red underneath the substation boxes. That's because it's getting that second return and bouncing back up to the sensor. So we're getting a little bit there. You would see more if we had more vegetation. But now going back into height, it's very easy to understand where all of those lines are, which you would not be able to model very well with a photogrammetry. And you can see if there's any sort of vegetation encroachment. Some other aspects of this, DJI Terra has tools to optimize the point cloud accuracy, to be able to clean up some of the points with the point cloud effective distance. You can output it in a known or arbitrary coordinate system. You can select what type of point cloud you want. LAS is pretty common, but also PLY, PCD, and points and S3MB. A lot of information, but we're going to next talk a little bit about the different use cases for LiDAR, but I'll pause here. Go ahead and take a screenshot if you want some specifications of the L1. Also, looking at the L1 versus photogrammetry solutions, ultimately it's just down to, do you want a good LiDAR point cloud or do you want photogrammetry? There's obviously advantages to L1. I would say anything that's going to be thin structures, very hard to map or model, so wires, just thin objects, vegetation, trying to get penetration through vegetation. If you're trying to do any sort of topography or digital terrain mapping, rather than just surface mapping, you're going to want to use an L1. Some typical frequently asked questions. We can run through these very quickly. We already talked about the recommended parameters for the L1, But just know that we do have an L1 operations guide out there. Just go ahead and Google that, DJI L1 operations guide, and it's going to help you a lot. I would highly recommend. Why is the IMU calibration necessary in flight? We need that to have a really accurate output. We need to understand exactly what the payload is doing during flight and then calibrate it multiple times during flight. So we kind of start from base 0 in those locations to be able to, when we load it into Terra, have very accurate strip alignment so we're not off a certain amount or have weird pitches within our strips. What's the field of view of the L1? It's right around 70 degrees horizontal. What's the difference between repetitive and non-repetitive? So kind of doing a line scan comparative to just capturing as many points across the entire horizontal and vertical field of view. When using the L1 and M300 PPK, or M300 is PPK supported. It is just when you load in the SD card from the L1, within the folder that you captured, there will have all the GNSS observation data and the exposure logs and everything like that for PPK corrections. All right. We'll talk through a couple different applications and use cases, but overall, like we talked about earlier with LiDAR versus photogrammetry, it's going to be able to help capture that topographical survey, much more accurate DTMs versus just DSMs. Infrastructure reconstruction, so thin structures, you know, sites with construction, but their active construction have a lot of scaffolding and things like that are really hard to stitch with just imagery. And so infrastructure is going to be common, forestry as well, to understand, once again, digital terrain models, understand vegetation canopy, and then emergency mapping, since you can stitch that point cloud real time with the L1 and it takes a lot less time to process the data compared to photogrammetry. You can utilize the L1 for emergency mapping. So a couple different case studies. You can see the original LiDAR data, then processed into some tree classification, and then getting into the elevation model on the bottom right-hand side. A little bit of background on this site. They used the Matrice 300 RTK with the L1 and turned it on dual return, and were able to get a really accurate topographical map. Basically, they just process the data, output it as an LAS, and then use the third party to do some feature extraction. Pretty commonly, that's going to be something like Terra Solid. Detailed bridge inspection. Bridge inspection is going to be a very important aspect for L1. So if we're looking at the actual road surface, obviously LiDAR is going to be potentially more beneficial than photogrammetry because you're going to be able to get LiDAR penetration into those cracks for crack detection. Also with all of the guide wires there, to be able to map and model those guide wires with LiDAR would be much faster, and photogrammetry would be really hard to get a clean output. Also, a good shout out for why you'd want to have a gimbalized LiDAR unit to be able to do the scans of the different sections of bridge, those support sections, so you could actually gimbal up and do a facades inspection up that support rather than only just doing top down with a lot of different LiDAR units. Talking about thin structures to be able to map and or model, we're able to use the Matrice 300 and the L1 with terrain following to use power line inspection. They did a corridor flight plan. It was a very quick mission, and you still are able to very easily understand. Looks like there's about one section here where we might get some vegetation penetration where they'll want to go check, but the rest of the site looks pretty clean, and we're under our thresholds for line sag. So. And then oil and gas, a lot of pre and post flight surveys are going to be done with LiDAR. You know, those the locations that they're at, they have a lot of critical infrastructure going to those locations to set up for drilling. And they need to be able to understand the topography and understand the environmental impact on that location. And so utilizing LiDAR to get a good digital terrain model, to understand drainage, to understand if there's any pockets within the soil that may cause problems, they're able to go over and have a really, really accurate elevation map from the L1. It kind of goes the same here for the geothermal energy side, doing large topographical surveys for elevation modeling and vegetation mapping. Doing some right-of-way analysis as well. We talked about right-of-way analysis with telecommunications, but yeah, a lot of the same use cases. And then finally, kind of finishing up, Frontier Precision and Houston Engineering partnered up and utilizing the L1 payloads to be able to map and model critical infrastructure. So those sites, mainly roadways, that they're going to be able to go out there and scan and understand and remodel those. While two main factors. One, they're going to be able to do it much quicker so they can keep people off the roadways, so it's much safer. And two, the outputs were much better than what they were using with traditional scanning. Ground-based laser scanning was taking much too long, and they weren't getting a dense enough point cloud where they absolutely needed it across the entire site. And then the safety perspective. So really good job there with Frontier and Houston being able to utilize LiDAR for a lot of road inspections and being able to be very quick and prompt and getting great outputs from those. And that's it. We've walked through the Zenmuse L1 solution. What are all the different components on it? What are some of the features that we have and why we would want to be selling it? Why it's an all-in-one solution. We talked about processing the data within DJI Terra and some of the different flight modes you have. We also talked about recommended parameters before you process that data, recommended flight parameters, and then we also talked about finishing up with the different case studies and why you'd want to be using LiDAR for some of those different sites. So if you have any questions, feel free. Reach out to me at any point. We're happy to get you any answers that you may need. And from the DJI Solutions Engineering team, thank you very much for joining.